Welcome back. This is the continuation of Section 3 from Chapter 1, Earth's Orbital Motion. I'm going to start this lecture actually with a question. What month of the year is Earth closest to the Sun? What month of the year is the Earth closest to the Sun? What do you think? I can tell you the most common guesses in class would be June, July, and August. What specific month are we closest to the Sun? Well, the correct answer is January. Yeah, January. Sure is. Specifically January 4th. January 4th. Take a look here at this picture on the screen. This is how large the Sun is in the sky at two different times of the year, in July and January. First of all, the first thing you should really notice is it's just about the same exact size in the sky. Why? Because the Earth's orbit is almost a circle. Yeah, the Earth is almost the same distance from the Sun all year round. Now, the reason people guess, of course, June, July, and August, at least here in the Northern Hemisphere, they guess that because that's when it's hot. That's the summertime. But remember, what is it that causes the seasons? It's the Earth's tilt. It's the tilt of our axis. If we're tilted towards the Sun, it's summer. If we're tilted away from the Sun, it's winter. It's all about the tilt. It's not about how far the Earth is from the Sun. And it just so happens we're actually slightly closer. The closest on January 4th. That's what's called our perihelion. Helion means sun. So perihelion is just the closest point to the Sun. Aphelion, as you see at the bottom there, I always think aphelion, I think away. Away. And at aphelion, it's on July 4th is when we're actually farthest from the Sun, oddly enough. But again, it's a very, very slight difference, as you can see from the picture. Anyway, I mentioned there it was our tilt. The Earth actually tilts 23.5 degrees, kind of a basic number everybody should know. That is the tilt of our planet Earth. And now if you take a look, hopefully at the cursor here, where did it go? There it goes. Here in June, in the north, we're tilted towards the Sun, and that's our summertime. You notice we keep the same tilt as we go around the Sun. Same exact tilt, except now, when we're on the opposite side of the Sun's rays are hitting in the southern hemisphere, and it's our winter in the north. That's all that's happening. We go around the Sun. We always keep the same tilt as we go around. It's just where the Sun's rays hitting most directly. And when the Sun's rays are hitting at the equator, that would be our fall and spring. Specifically, when it's right on the equator, we call that the equinox, in both the fall and the spring equinox. All right, what are some other things affected by our tilt? Obviously, the seasons. We already talked about that. When the Sun, let's say here in the north, when it reaches its highest point on the globe, around June 21st or so, that's our summer solstice. And of course, when it reaches the southernmost point on the globe, for us, that's winter. So that would be our winter solstice around December 21st or so. Now, some other things that are affected there. And I mentioned here at the equinox that you also have, the reason it's called equinox actually, is that you have equal day and night. It's not quite exact, but anyway, that's what you can pretty much think of. Okay, equal day and night on the equinoxes themselves. That's where the Sun is crossing. Its most direct rays are crossing the equator. But there are other things that are affected as well. And especially if you live up north, if you live really far north, you start noticing these things a lot. How high up the Sun is in the sky. I pay attention to this a lot now that I have a solar panel out in our garden. It's kind of interesting to think about the angles there of the Sun. Here's something that'll surprise you. I live in South Florida. There is not a single day of the year when the Sun is directly overhead. Not a single day of the year. Now, why is that? Well, because even at the summer solstice, the Sun has its rays have gone up to 23.5 degrees on the equator. By the way, we call that the Tropic of Cancer. 23.5 degrees. But South Florida, exactly where I'm at in the Coral Springs Parkland area, is at 26 degrees. So yeah, it's a couple degrees off of our zenith. It's not quite directly overhead, though. I mean, I can actually say that it's not quite, by a couple degrees, it's not directly overhead. And the farther north you go, the more pronounced this difference is. Let me show you a picture. I'll come back to this page in a second. Here's what you see when you live up north. Let's take a look real quick. And I grew up in Illinois, and when I go back home now, I pay attention to this kind of thing. We'll go out and have our winter family football game, and it's noon, and I'm looking, and the sun is really low in the sky. People don't really pay attention to this at all. They just don't pay attention. You know, ancient people paid attention to the sky all the time. We're all busy with other things and have our face in our phones, and we don't notice these kind of things. But look at that. Now, wherever this is at on the earth, you see that's the sun's path during the day, and it's just not getting very high up in the sky. Of course, that's going to affect the length of the day, right? The sun, it's not going that far in the sky, so the sun is not out for very long at all. And here's what happens during the year. So let's say it's our summer solstice here in South Florida. Longest day of the year, right? The sun is going to rise almost directly in the east and get almost directly above our head and set almost in the west. I mean, close enough that we're going to think with our eyes that it's rising in the east, going directly overhead at noon, and setting in the west, okay? But now, from that moment on, day after day, the sun starts drifting southward. It's drifting away from us. And I'll notice this on my way to work. I pay attention to where the sun's at in the sky as I go to work, and it's really interesting to watch it cross from the Sawgrass Expressway down to this canal, down to this park, and I'm noticing it drifting away. And of course, ancient people noticed that, and it kind of freaked them out. And they really were concerned when it got to be the winter solstice, when the sun had gone as far south as it was going to go. And it's probably when they had a lot of their ceremonies and things like that. We know this for a fact. Probably celebrating, but also concerned, hoping the sun would come on back. They probably got concerned as the days got shorter. Hey, here, and they're noticing the sun drifting. They probably got concerned. That's why a lot of holidays are actually around those particular times, like the winter solstice around the 21st. It's how Christmas came to be around that time period, and so forth. But anyway, all right. So a lot of things affected by the Earth's tilt. Keep the same tilt all year round, though. 23.5 degrees always. Just depends on where the rays are hitting. Well, here's something fun. Now, everybody learns that kind of thing in elementary school. Precession is pretty neat. If you spin a top, and you spin it pretty fast, and it's just sitting there spinning, what starts to happen? Well, after a minute or so, it starts to wobble. Spinning things wobble. And guess what? The Earth is a spinning thing like a top, and we wobble. Yes, we call it precession is the fancy term, but it's just a wobble. Now, how long does it take the Earth to wobble? Well, quite a while. It's a 26,000-year wobble. Yeah, that's a pretty long wobble. So this is not something that affects you during your lifetime at all whatsoever. But it's kind of interesting. Let me explain some effects it would have over a very, very long period of time. Couple things. Our calendar would get kind of messed up over time. Here's where it's kind of neat. As the Earth wobbles around, if you take a look at the picture, no, I'll get to the picture in a second, actually. I'm sorry. But if the Earth is tilted this way, and let's say that this represents the summertime, eventually the Earth will go around, and as we wobble during that same time period, we'll be facing the other way. Let me get my hand right there. All right? We'll be facing the exact opposite way. Now, how long would it take to be facing to wobble around? Well, it'd be half a wobble, or 13,000 years. So check this out. In 13,000 years, June will be the beginning of winter. Yeah. The months drift through the different seasons. June will be a fall month and a winter month and a spring month and so forth. All of the months shift around over enough time, over thousands and thousands of years. And then the other thing you can notice here in the picture, as we wobble around on our axis, right now, the Earth's axis, the northern axis, happens to be pointed almost exactly towards a star called Polaris. Just by coincidence. Pretty bright star. Well, there are going to be a lot of times when there is no North Star, as you're about to see, and eventually will be pointed towards other stars like Vega. I'll show you that in one moment. So our North Star does change over time. To put an example down there, if you're one of my students right now watching this lecture, Thuban, Thuban, is an example of a North Star that was used by the ancient Egyptians, for example. At the time they're building the pyramids, they're actually aligning the shafts of the pyramids with Thuban, because that was their North Star. Thuban is a star in Draco. So here's what it looks like over enough time. It's kind of cool. If the Earth had no tilt whatsoever, we'd be pointed towards that X right there in the middle of Draco. But a 23.5 degree tilt corresponds to that yellow circle that you see. And every one of those tick marks represents 1,000 years. 1,000 years. So check it out. Right now, here we are, right there in that part of the yellow circle, pointed toward Polaris. That's the year 2000, that tick mark just to the left, right there, just to the left of Polaris is 2000, year 3000, 4000. So these stars right here in Cepheus, I mean, maybe we'll use them as North Stars, but they're not very bright stars. Then you have a section here at 8000 AD. We just won't have a North Star. There's just not a good one. We might use Deneb eventually. We might use Vega. Where's this cursor going? There we go. Deneb, Vega. They'll probably be counted as the North Star someday, even though they're not exactly on that yellow circle, so they're not very good. They're bright, but they're not really on the circle. And then look at this. You get to these years, thousands and thousands of years, where there is no North Star. And then look at this. There it is, Thuban. So Thuban was the North Star for the ancient Egyptians, and it will get its day in the sun again in the year 24,000 AD. In 24,000, Thuban will be the North Star again. And of course, eventually Polaris will be the North Star again after one complete wobble, which takes how long? 26,000 years. 26,000 years. Kind of interesting stuff. Kind of trivial, but still neat. One last thing here. We do things in class, by the way, where we do computer interactives and things to help understand the seasons and so forth. It's kind of hard to explain everything here without a model. So check this out. There are two different types of day. I bet you didn't know this. Two different types. There's a sidereal day and a solar day. A sidereal day is how long it takes the Earth to spin on its axis. Most of you are thinking, oh, it takes 24 hours. Wrong. Wrong. The Earth does not spin on its axis in 24 hours. The Earth spins on its axis in 23 hours and 56 minutes. Yep, that's a sidereal day. That's measuring a day with respect to the stars. So what's 24-hour day? Well, 24-hour day is based on how long it takes to go, let's say, from noon to noon. Starting, hundreds, thousands of years ago, I should say, when you had sundials and things like that. And eventually we decided to chop up time into hours and so forth. But the point being, it was based on the position of the sun. Now, why are those two things not matched up? Well, there's one basic reason. And obviously a 24-hour day is really close to the 23 hours and 56 minutes it takes us to spin around. But why aren't they exactly the same? One reason. Because during the time that the Earth is spinning on its axis, guess what else it's doing? It's moving. It's moving around the sun. So take a look at the picture here. Here you are at point A on the Earth. And look where the sun is. It's directly over your head. Now, if you spin around one time on the axis, look at this. Same angle. You're at point A. 23 hours and 56 minutes later, you've spun around one time. But look. The sun is no longer in your path. The Earth has to spin just a little bit more until the sun's overhead again. How much more? 4 minutes. 4 minutes of time to spin because the Earth has moved while we're spinning, and that throws things off just slightly. Yes, I know it's kind of trivial and so forth, but that's, again, makes this class a little more advanced than something you learned in middle school. So a sidereal day, how long it takes to spin on the axis, that's 23 hours, 56 minutes. A solar day, which is what we base our time on, is 24 hours, of course, and that was based on the position of the sun. And we'll talk about the moon next time. Thanks for listening.